All right, thank you very much. Thank you for inviting me to give this talk, and thank you to the organizers for all your hard work in putting together this workshop. It's great to see so many people back together again. Hopefully the era of online conferences is behind us. So today I'm going to tell you about some work that has not yet appeared, but should appear shortly with Mikhail Solon on taking relativistic scattering amplitudes and turning them into classical gravitational n-body potentials, where here n is some number bigger than 2. Okay, so the basic motivation behind this is one of the oldest and best studied problems in all of theoretical physics, which is to understand the motion of n gravitating bodies. So the nature of this problem sort of changed in an interesting qualitative way in the 20th century when we learned that our universe was described by general relativity. So in the Newtonian version of this problem, because Newtonian gravity is a linear theory, the way that that shows up in this is that the n-body potential that enters the equations of motion is just a sum over two-body pairwise interactions. So body 1 experiences forces from bodies 2, 3, 4, and 5, body 2 from bodies 1, 3, 4, and 5, and so on. Einsteinian gravity, general relativity, is qualitatively different in that it's a nonlinear theory. The n-body potential is also a sum over two-body pairwise interactions, but additionally there are intrinsic 3-body, 4-body, 5-body, etc. Terms that appear in the effective potential. So this is, for example, what the leading order effect of this kind, it was computed long ago by Einstein, Infeld, and Hoffman, looks like. It's some order g squared piece that depends on the coordinates of 3 of the bodies at the same time. And this is qualitatively new. So what this talk is about is extending this framework that many people here are experts in, and we heard a great introduction from Julio on Tuesday, which is this framework for using collider physics methods to calculate classical potentials, but extending that beyond the two-body problem to the n-body problem. So what I'll try and do is not just tell you about some new results. I'll also try and give you an overview of a general framework for doing these calculations and the various challenges that arise that are different from the two-body problem. So there are new features that only show up when you have more than 2 bodies. In terms of explicit results, what I'll present is an explicit calculation of the second post-Minkowskian, or order g squared, 3-body potential in general relativity, and also in the Einstein-Maxwell theory, so black holes with charges. And I'll explain later why we did that calculation. Unfortunately, what this talk is not about is solving the n-body equations of motion. And there are many interesting things that you can say here, which I am definitely not an expert in. So interesting questions about numerical solutions, finding exact solutions, post-Newtonian corrections to well-studied features of the n-body problem like chaos and so on. It's also not about the astrophysics of n-body systems. This is, again, something I'm very much not an expert in. These things show up in various interesting astrophysical scenarios involving dense star clusters, hierarchical black hole triples. People have discussed post-Newtonian corrections to Kozai-Lidov oscillations and other things. And so, in fact, to head off a question that I'll inevitably get, let me say this is my question for people here who are much more on the phenomenological side. It would be nice to have a better understanding of exactly what which post-Newtonian corrections to n-body dynamics are possibly observable with the new generations of gravitational-wave detectors and other things in the future. But today I'm going to focus mainly on the theoretical problem of calculating these potentials. Okay, so let me start with a fairly naive question just to set the framework. So suppose I wanted to calculate, suppose I wanted to do a simulation for some n-body system where n was some very large number. This is not crazy, this is something people actually sort of do, where n is, say, 10 to the 6. If I wanted to calculate that from some potential, do I need to first calculate a 10 to the 6 body Feynman diagram? The answer is no. Even without understanding in detail how these potentials are obtained, there's some rough correspondence between Feynman diagrams and n-body potential pieces, where the leading order contribution to the 2-body piece comes from a tree-level diagram, from the 3-body piece from a 3-body diagram, the 4-body piece from a 4-body diagram, and so on at tree level. And so you can see that they enter, the first contribution that they have is at some g power that is determined by the number of vertices in the corresponding tree diagram. So for tree level, there's 2 vertices. Each vertex comes with the factor of square root of g, and so you get an order g contribution, which is Newton's law. The leading contribution for 3-body enters at order g squared, for 4-body at order g cubed, and so on. And so if what you're ultimately interested in is doing some simulation at fixed post-Newtonian order, even if n is some crazy high number like 10 to the 6, once you fix a post-Newtonian order, you only need to compute your scattering amplitudes up to some much, much lower multiplicity number. So this is a subject that has a very long history. Let me tell you about what the state of the art of this problem is. So the 0pn piece of the potential was computed by Newton, or was written down by Newton. And in this Feynman diagram language, this corresponds to a tree level calculation. The first post-Newtonian piece was calculated by Einstein, Infeld, and Hoffman. Again, in this language of Feynman diagrams, there's a contribution for the 2-body interactions that enters at 1 loop, and the 3-body interactions that enter at tree level. And then the sort of state of the art as of today in terms of complete calculations is 3 bodies at 2pn, where the complete 2pn calculation up to 3 bodies was completed by Schaefer in '87. This corresponds to a 1-loop 3-body calculation, a 2-loop 2-body calculation. And then if you want to extend this to n bodies at this order, there's another piece that you would need, which is the static or tree level contribution of 4-body interactions. And this is actually not known. It's partially known up to some unevaluated 2-loop Feynman integral. Now that sounds a little bit funny because I've said here that this is a tree level calculation. So why am I talking about loop integrals? And I'll explain as I go along why you actually end up having to solve Feynman integrals even to do tree level calculations in the subject. But this is sort of the state of the art. And so the question is, can we do better than this? Can collider physics methods help push the state of the art for n-body dynamics and general relativity? Okay, so the basic overview of how these method works is the same for n bodies as it is for 2 bodies. So let me just say in a few words the basic picture. The idea is to calculate the potential by computing the same object, a relativistic scattering amplitude, in 2 different formalisms, and then requiring that they are the same thing. So the first calculation is the calculation of a Feynman amplitude using, a calculation of scattering amplitude using Feynman diagrams, or the Feynman expansion. And then the second formalism is to compute it using what you learn in your sort of graduate quantum mechanics classes, which is potential scattering, which is to solve the Lippmann-Schwinger equation for some Hamiltonian order by order in the Born series. And then to require that these 2 things are the same when they're expanded in the limit of small momentum transfer. So in the limit where the gravitons inside of these Feynman diagrams are sort of very off shell, mediating approximately instantaneous forces and so on. So requiring these 2 calculations give the same thing to find some potential. In some equation, you have some equality between these 2 things, which a little bit more concretely is some equation that tells you that some Feynman amplitude is related to the Born series. And the idea is to extract the potential by matching these 2 things. There's some subtraction pieces that have to be removed because ultimately what we want is just the potential. There's some iteration of lower order pieces. This is all well known to people who have been doing this for 2 bodies now for many years. So we take this amplitude and we make some expansion in the small momentum transfer limit. And just as you do for 2 bodies, you find that at leading order, the pieces, if you do the careful h-bar counting, there are pieces that scale like 1 over h-bar, which in Q counting is in this 3-body problem, this tree level 3-body problem is 1 over q to the 5. So the fact that it's 1 over h-bar means we would describe this as superclassical. There, underneath those are the actual classical pieces that are order h-bar to the 0 that we care about. And then there are higher order in h-bar pieces that scale like higher orders of q that are quantum, and we throw those away as quickly as we possibly can because they're not relevant for the classical physics. So the slogan for the calculation of these n-body potentials is going to be more is different. So that means that I'm going to tell you that there are various ways in which this calculation is qualitatively different from the 2-body calculation, and I'll try and tell you what those features are. So the first way in which it's different is that there is a much more complicated iteration structure that has to be understood. There's no analog of isotropic gauge, and in general, there's a sort of chaos of gauge and making choices about how to write down your potential. And then the third way in which it is different, and potentially one of the biggest computational bottlenecks, is that it involves calculating non-trivial n-body Fourier transforms. Okay, so let me start with talking about the iteration contributions. So the momentum space, three-body Hamiltonian, it has this general form. So once you Fourier transform to momentum space, you have your two-body potential and your three-body potential pieces, and they come with various delta functions, which just enforce various momentum conservations at various places. If you plug this thing into your next to leading order term in the Born series, which basically means to take the product of two potentials and then do some phase space integral over the intermediate states, you'll find that there's some piece where these delta functions here localize all of the integrations, and you end up with something that has an effective tree topology. So this is something that doesn't show up for the two-body problem at all. The iteration structures look like bubbles after bubbles after bubbles. But for the three-body problem and higher, you get these sort of EFT tree-level diagrams. So this unfortunately causes an immediate problem, or it means you have to go back and compute something at two-body that maybe you didn't know, which is that the input to computing something like this is some two-body potential for particles with momenta P1 and P2. And the sort of standard thing that people have done in this problem is to immediately go to the center of mass frame and do the calculation there, where things are a lot simpler for reasons I'll explain in a second. But that's clearly not going to be good enough for input for the three-body problem. Even if you choose P1 and P2 to be equal and opposite, then the two momenta that go into the second vertex are no longer going to be in the center of mass frame, and so on. So what you need is the two-body potential in a general frame as input for the three-body calculation. And then obviously this will just continue on to higher orders. So the three-body potential in a general frame is needed as input for the four-body calculation, and so on and so on. So you really need to do these calculations in a general reference frame. And one reason why this makes life a little bit complicated is let's go back for a moment to the matching of the full theory Feynman amplitude for a two-body process to the potential. So in detail, the equation that you're matching looks like this. And written out in this explicit form makes obvious a fact that's otherwise seemingly a little bit paradoxical, which is that the object on the left-hand side, the amplitude, is gauge invariant, but the potential that appears on the right-hand side is not gauge invariant. And the way out of this paradox is this energy conserving delta function here. The source of the gauge non-invariance of the potential is the fact that you can add to the potential any piece which vanishes on the support of this energy conserving delta function. So there's some expression that you basically can add any multiple of this thing times any function to your potential, and you get a physically equivalent potential that's computed in some different gauge. In position space, this is equivalent to just changing to some change of coordinates. It may be very complicated. You may not know what it is, but it's some change of coordinates. And so the way that people sort of historically use this freedom is that they spend it by first going to the center of mass frame, which means to pick your two incoming momenta, P1 and P2, to be equal and opposite. And then if you make that choice in this expression, you can use this ambiguity to kill all dot products of the form P dot Q. So this is what people call the isotropic gauge, and it dramatically simplifies the two-body potential. But what I'm telling you is that for input for the three-body problem, you can't do this because you can't go to this frame. So the next best thing that you can do is you can do something which is as close as possible. So you work in a general frame, and you can use this freedom to rewrite all your dot products in terms of one dot product, which is basically the total incoming momentum dot Q1. So in sort of gory detail, what this does, for example, to the 1 PM, so the tree level two-body Hamiltonian, is that it changes the graviton pole structure by adding a piece that is basically a kind of energy transfer, a Q0. And this is the sort of thing that feeds into the iteration calculations and makes things very complicated. This continues to higher order. There's a similar ambiguity for the three-body potential. Here you have the same ambiguity. You can add pieces that are proportional to the energy conservation expression. So here's one example, but there are actually infinitely many, with any coefficient you like. And that makes this three-body potential sort of infinitely gauge redundant or ambiguous. And so trying to compare against some calculation your friend does is very challenging. There's no apparent canonical or best choice, simply because there's way more freedom than there are constraints. Even picking good, even if you do pick a frame, it doesn't help you very much. And so you just have to live with this. And so in terms of practical calculations, if you want to compare to other people's results, what you typically do is you calculate a gauge-independent observable, like a classical scattering amplitude or a scattering angle. This is related to a part of the calculation of the iterations. So the sort of non-trivial part of that calculation is you take some full theory graph and some corresponding EFT graph, where the correspondence is in the sense that these have the same singularity structures. And though naively you would think that maybe these two things are sort of equal and opposite and will cancel each other, there's actually an imperfect cancellation. And the reason that there's an imperfect cancellation is because of these non-trivial energy transfer pieces that turn out to be different in the full theory and the EFT. So you get so ignoring some numerator structures, you basically end up with some singularity structures like this in the full theory side and on the EFT side. And this isn't an artifact of making some bad choice in your calculation. No matter how you choose the gauge, something like this is going to happen. And so there's a sort of art more than a science to write down a potential that manifests two properties at the same time. One is the cancellation of this matter singularity, which is this sort of internal matter line has some singularity that shouldn't be there in the final potential. And the second is that there's some superclassical pieces of both of these that have to cancel against each other. And there's some art to making this, to writing expressions, to writing this difference in a form that has both of these properties at the same time. So the systematics of this is understood at order g squared, so at tree level, but it's more challenging at one loop, and this is work in progress. In the one loop case, this sort of misalignment of graviton poles shows up at the level of integrands for sort of one loop iteration pieces. Okay, the final sort of new feature about this, about the n-body problem that is potentially a serious bottleneck, is that what I've told you about so far is actually calculating the potential in momentum space, but what we really want is the potential in position space. For example, I want to hand to an astrophysicist a potential in position space so they can do a simulation. So you have to do a Fourier transform. Directly Fourier transforming the post-Minkowskian expressions may be too difficult, and so perhaps the best we can do is to do a velocity expansion before integration. So this is the kind of thing that shows up for this three-body at tree level, is you get some Fourier transform of some expression that has three graviton poles in the denominator and a delta function enforcing momentum conservation in the numerator. And with a little bit of trickery of rewriting this delta function as an integral over an auxiliary point, this turns into a Feynman integral. So this is an ordinary-ish looking Euclidean triangle integral where you're integrating in 3 dimensions with the obnoxious feature that these, what would be Feynman propagators, are raised to half integer powers. At one loop for 3 bodies, you get a similar thing, but now one of your propagators is raised to the 2nd power, and then for 4 bodies at tree level, it turns into a 2-loop Feynman integral. So I said before that the 4-body 2pn calculation was unknown in closed form, and that's because this integral has never been evaluated. So this is one place where I think actually Amplitudes people can make progress in this subject, which is understanding this sort of interesting class of Feynman integrals. Okay, so the sort of Feynman integrals we need for the 3-body problem are things like this, where these things are raised to sort of arbitrary powers, alpha 1, alpha 2, alpha 3. For a certain class that's relevant for the tree level calculation, these were a general approach to calculating these was found in this nice paper by Jan and friends. They sort of, roughly speaking, the answer looks like this, or this is a sort of basis of functions that you find. Now you may wonder, you may have seen an integral like this somewhere in a textbook or something, maybe one of Smirnov's books, and so you might wonder actually if isn't this known in closed form? And the answer is sort of yes. So this integral is sort of computed by Booz and Davidichev long ago, where the answer is given in terms of some hypergeometric function, who in this context that depends on some ratios of distances. the problem is that this, if you actually dig into the definition of this Appel F4 function that shows up, it has a region of convergence, which in terms of these arguments means that it's only that the series that defines this function only converges when R12, the distance between bodies 1 and 2, plus R13 is less than R23. But if you think about for a second that these are actually the distances between physical objects in space, you'll recognize that this is the triangle inequality, but with the inequality sign flipped the wrong way. So what that means is that this function, this formal answer to this integral, converges on the complement of the physical region. So it's actually nowhere convergent where any actual physics takes place. And so the challenge is to either analytically continue this answer or to just compute these in some different way. So one thing that we did to sort of make progress in this, in lieu of having sort of exact answers to these integrals, is that you can construct a new convergent series expansion which makes use of a sort of physically relevant special case of the three-body problem, which is the so-called hierarchical limit, where two of the bodies are close together and the third is very far away. And so you have some small dimensionless ratio that you can do expansions in. And you can evaluate these integrals using the method of regions. So another tool that comes from the collider physics world. So you can take these integrals that you don't know, and you basically get three different regions, one where this x0 point is inserted near the two bodies, a second region where it's inserted near the far body, and then a third region which is scaleless, where it's far away from everything. And you sum that up and you get some series expansion that you can compute to whatever order you like. So this may actually be the way to get explicit position space expressions for higher orders in PM for three-body. Of course, it would be better to have exact expressions, but this may be the best we can do. So these expressions by construction converge in the physical region for generic values of these powers alpha. And they provide all the necessary Fourier transform integrals at order g cubed in this hierarchical limit. Okay, so without further ado, let me show you what the final expression was for this, this tree level calculation that we did. So the general form of the Hamiltonian, again, it looks like this. There's some two-body pieces that we computed in this generalized isotropic gauge. And then the important thing are these three-body pieces. So let me present it in two halves. So the first half of the calculation corresponds to straightforwardly these two Feynman diagrams, which don't have any internal matter propagators. And in this case, there's nothing difficult about it. It's just take the Feynman rules for those graphs, write them down, and expand to the classical order, and you get the expression. The more interesting piece is the subtraction between the full theory diagrams that have matter propagators and these EFT iteration pieces. And there's some manipulations you need to do, spend your gauge freedom in clever ways, and you can write down an explicit answer that has no matter propagators and is manifestly classical order. The price you pay for this is a sort of doubling of the graviton poles, where you have terms that contain basically a graviton pole with one energy prescription multiplied by the same graviton pole with a different energy transfer prescription. But the answer is completely explicit and has all the physical features that you would like. Okay, so how do we know that this extremely complicated result is correct? So the first set of checks that we did was that we took our expression and we compared it with the post-Newtonian results that were available in the literature. So this is the second post-Newtonian Lagrangian. So it's not quite the same thing we're calculating. We're computing a Hamiltonian. But this comes from this nice paper by Jan and friends, although it's equivalent to some older things that were already known. The state of the art is one order above this, but it's too big for me to write on a slide. If you actually write out the whole thing, it's about 5,000 terms long. So what we did was we took these Lagrangians and we Legendre transformed them to Hamiltonians, and then Fourier transformed them, and then turned them into scattering amplitudes, which should be gauge invariant, and then compared them to our result. And we found perfect agreement up to this order. In fact, this paper actually computes in some sense the post-Minkowskian answer, so the same thing that we calculated, but it's sort of in a form where if you want to turn it into a scattering amplitude, you have to do a certain amount of unpacking, and this was only done explicitly up to this order, but in principle you could go higher, and I think you would be likely to find agreement. So this is a very complicated sort of comparison. you might wonder if you focused on some special limiting cases, it's a bit easier to see that this is correct. So this is a common strategy people do in the two-body problem. You might wonder if some part of this horrible answer is fixed by the probe or the test mass limit. So there's a simple test mass kind of scenario you can imagine where you basically have one large Schwarzschild black hole and then two smaller objects, which could be moving relativistically. And you can write down a Hamiltonian for this system, and you do find agreement, but it's trivial in the sense that in the strict test mass limit for these two objects, there's no three-body information at all. Basically, these two test masses don't talk to each other at this order. There is an interesting calculation you could imagine doing that I don't know if anyone has done, which is to take a three-body system like this and compute the first self-force correction. I don't know how to do that and turn it into a Hamiltonian, but in principle, you could imagine computing the motion of body 2 in the sort of first-order back-reacted geometry of bodies 1 and 3 and vice versa, and then see if you get agreement in that case. So what you need to do an interesting probe limit calculation is you need multi-center black hole solutions. Unfortunately, these don't exist in pure general relativity, as far as I know. They only exist if you extend your theory by adding electric charges. And so what we did, because we thought this was very interesting and we wanted to be absolutely confident that what we were doing was correct, we extended our calculation to include charged bodies in Einstein-Maxwell theory, which basically means redoing the calculation with not just having gravitons as internal lines, but also photons as internal lines. And so if you do that, you have access to these wonderful solutions that were found long ago by Majumdar and Papapetru that describe multi-center black hole configurations where you have actually n, as many as you want, extremal black holes sitting there in space-time in exact static equilibrium, where there's a cancellation between the gravitational attraction and the electrostatic propulsion. And so what you can do is you can take these Majumdar-Papapetru solutions and put a charged relativistic probe, make your third body a probe, moving on this background, and turn this into a probe Hamiltonian, which is some formal expression like this, that's all orders in g and velocity. Expand this out to the order that you can compare it to, which is order g squared, but keep all orders in velocity, and you genuinely here find three-body interaction pieces. Unsurprisingly, there's some piece that where all three bodies talk to each other. And then you can turn this into a scattering amplitude and compare with our Einstein-Maxwell Hamiltonian, compute it to the same order, and to leading order in the small mass ratio, but at order g squared and all orders in momentum, you find exact agreement. Finally, there's another related kind of check that you can do that is along the same lines, which is that you can imagine that all three of your bodies are electrically charged extremal black holes. And there was a very interesting calculation that was done by Erdely and Ferrell here, actually, at UCSB a long time ago, where they basically took the Majumdar-Papapetru solution and they perturbed around the static solution order by order in velocity and kept everything to leading order in V. And if you do this, you can turn this into an effective Lagrangian that is only valid at leading order in velocity, but is exact in g Newton. So it's an effective Lagrangian that's valid even in the strong field regime, where the sort of the separation between the black holes is sort of order their Schwarzschild radii, which in scattering amplitudes language means that it has information in it that is all loop orders. It's sometimes called the moduli space approximation. It has to do with the idea that you should think about this as a 0 plus 1d sigma model. I probably won't expand on that. But anyway, you can take this wonderful formula that fits on one line and you expand it out to order g squared, and you take our answer and you expand it to the same order and also leading order in momentum, set all the charges equal to the masses, compute a scattering amplitude, and you find exact agreement. Okay, so I'm about out of time, so let me conclude. What I hope I've at least tried to convince you of today is that n-body classical gravitational dynamics are an exciting new direction for collider physics methods. The slogan, to borrow Phil Anderson's phrase, is that more is different. There are new and challenging aspects of this problem that only appear for the first time for greater than or equal to three-body interactions. And I think our community is uniquely well suited to meet these challenges and to push the state of the art. For example, to calculate these higher order Fourier transform integrals, and also to think about clever ways of organizing these iteration subtraction pieces and things like this. There are many future directions. The addition of spin degrees of freedom is something that's relatively unexplored. Focusing on hierarchical systems might be a way of making a lot of progress, and other things like this. But thank you very much.
Okay, thank you, Callum. Questions?
Great, thanks. I'm just wondering, is there a way of like bypassing the whole Hamiltonian in like having some analog of this boundary to bound mapping, for example, for three bodies?
I do not know if you could generalize the boundary to bound dictionary to three bodies. Possibly. There are certain, let me just make a comment about bypassing the Hamiltonian. So there are certain observables that if you wanted to obtain them, you would not compute a Hamiltonian. So for example, if you want to compute a scattering angle, so it's sort of a little bit hard to imagine, but you can imagine what's the scattering angle for, say, body 1, you know, as fixing the incoming momentum of bodies 2 and 3 or something. That's a quantity that you wouldn't compute a Hamiltonian, this horrible Hamiltonian, and then compute that by solving classical equations. You'd feed it into something like K-Mach. You would do the whole calculation using gauge invariant objects the whole way, and then you could avoid all of this. For things like binding energies, I don't know, but it is possible.
Okay, there were some questions over here.
Yeah, thanks, Callum, for a very nice talk. It's also comforting to see that our calculation was sort of checked by yours now, that we agree on this. One thing we struggled with was exactly the question you just alluded at. What are good observables in this problem? So could you expand a bit on that? I mean, I
mean, coming from a scattering amplitudes perspective, the observables that I know how to calculate that are gauge invariant are always asymptotic. But I feel like these are not what an astrophysicist cares about. They want to do like a real-time simulation where they have n bodies in a bound system. In terms of how do you get a gauge invariant observable out of that? I mean, I really actually don't know. This is something I'm hoping astrophysicists can tell me. I mean, did you guys think about this?
No, I mean, it's a chaotic system, so we were also thinking about bound configurations. So it's not even clear. I mean, you know, bound doesn't even make sense.
Right.
A second question. I mean, now that you went through this computation and you also, you know, looked at ours very concretely, do you think, I mean, what's the advantage of going through the amplitudes in the end? Isn't it more efficient maybe to work with the world line?
Yeah, I mean, it's sort of not clear to me which one. There are sort of pluses and minuses on both sides. So the advantage of the amplitudes calculation is that it gives you a Hamiltonian, which well, so the thing that the world line calculation didn't give was a Lagrangian, which only has second order time derivatives. You sort of have these higher order time derivatives order by order in Pn that you then have to do some additional processing to get rid of, which I imagine at very high orders becomes extremely challenging. The amplitudes calculation gives you a Hamiltonian in, you know, so it's automatically like if you Legendre transform that, you get a Lagrangian that has only second order time derivatives. And so that's one reason. Of course, the negative is always that you have to deal with iterations and superclassical subtractions and things. And so at the end of the day, which one of these is ultimately better is something I think is not clear to me. Even in the two-body case, I mean, I think it's not clear.
Hey, thanks for a nice talk. So I just wonder if you can have another independent check, which is consider the hierarchical system you have. And if the two particles are really close, then it looks like an effective two-body potential. But one of them has like internal structure like spin or tidal, like quadruple moment. So if you can fix the effective action of that particle, the composite particle, then the rest of velocity series will be an independent check.
Yeah, I think I agree. I don't know how to do that calculation in detail, but I've seen things along those lines, sort of effective two-body Hamiltonians for three-body systems and things. I've seen things like this in the literature. We should chat about this afterwards, but I think that there is something like that you could do. And I think actually that's the relevant, and that may be the physically relevant case for gravitational waves, where sort of two of your bodies are sort of bound together in a binary, and the third one is like a supermassive black hole that's sort of far away. And so you're computing sort of perturbations to the binary system from the third body. So, yeah.
Thanks for the really nice talk. Are you aware of these axis-metric solutions which can have uncharged black holes along the axis in equilibrium at the cost, unfortunately, of some conical singularities along the axis?
It has like a strut singularity thing.
Because by arranging these, I think you could potentially construct some situations that you might also be able to test your results against.
Yeah, I am aware of these solutions. I guess you could do it. You could do a sort of empirical check, as you could take the probe on that background and compare it to the Hamiltonian. I would worry that like that strut singularity is somehow not in an amplitude. Like it's some extra like physical thing that isn't in the sort of three-body scattering amplitude that you're comparing against, and so you might not get a match. At least in the case of the extremal black hole solutions, I'm sort of very confident that that should match.
Right.
To some scattering of some extremal, point particles or whatever. But yeah, no, that's a good point. This is something that could be done.
Thanks.
So I was wondering about your Feynman-like integrals with where you had the non-integer powers of propagators. Yeah, and you said you would run into problems like having to do an analytic continuation of Appel functions. What was your conclusion there? Was that deemed to be too difficult?
So I mean, I don't know of how to directly do the analytic. In some sense, this, which is the exact answer, is the analytic continuation of this series evaluated for half, half, half. But in terms of actually taking the series and doing the analytic continuation directly, I don't know how to do that. So my approach would be to go back to the drawing board, go back to the start and try and compute the amplitude using a different method. So not to use Mellon-Barnes, which is how these guys computed it. But maybe some clever person could figure out how to take this series and continue it. I don't know how to do that though.
Okay. Oh, there's somebody on Zoom. Kanchan?
Yeah, hi. I just want to make a comment on this integral, this reward integral. So actually, we now think we have a closed form for this formula. We kind of extract it from a sort of, they call it triple K integral. So it's some sort of not just hypergeometric function, but I think we now have a closed form for this post-Newtonian integral. And
you mean for the general alpha 1, alpha 2, alpha 3 case? You have
for a half integer.
Oh, that's awesome.
Yeah.
But this is not in the literature. This is just you have it.
No, we haven't had any paper out yet. And there's another question. So in our paper, we sort of also have a post-Minkowskian potential, but as you were saying, it is not easy to extract anything from it because it's non-local in time. And your method seems like you are matching it, the amplitude result with the EFT result. So your potential seems like it's local in time. And my question is, do you think it's equivalent, or is there anything that you need to carefully check that they are completely equivalent to each other?
I mean, I think they're equivalent in the sense that if you compute a gauge invariant observable, you'll get the same answer. But they're definitely not computed in the same gauge. So trying to take our potential and compare it directly to yours, I don't know how that may not be possible.
Yeah, do you think that there are something like radiation reactions at this order, or is it going to appear only at the next order?
For 3 bodies, it would. I think it will only appear at the next order in G.
Okay, great.
I think you basically you just need you need a diagram with an external graviton. So you need an extra vertex. So yeah.
Okay, thanks.
Okay, see no further questions, so let's thank Callum again.